So, hey there, I am Ananya of MTech IT 4th semester. In this video, I will be explaining the section C of the first internal question paper of data science. So, in the first slide, I have written all the questions, in which the first question is discuss accuracy, completeness, consistency issue. And the second one is for handling missing value in extracted features. Discuss approaches like ignore tuples, manual completion, constant fill, mean, median, mode imputation, class specific imputation. The third question is smooth extracted scores. Use the evidence strength list from A to smooth using bin means bin def 3. Shows step B suggest ways to detect outliers. Discuss other smoothing techniques like bin, median. Discuss the schema integration and handling redundant entries. Explain the normalization method for feature scaling, min-max normalization, z-score normalization, z-score using mean absolute deviation, decimal scaling. Binning case severity scores are the data set is given. Partition into equal frequency bins, equal width bins, clustering based bins, and also explain implication for section mapping threshold. Feature selection for section mapping, summarize with flowchart the technique for choosing attributes used by the model forward selection and backward elimination, hybrid features, methods. So all these questions will be answered in next slides, which I'm going to explain. So answering the first question, we have, in order to enhance the data quality in legal analytics, it is paramount in legal analytics. Issues such as missing templates, so issues such as missing timestamps, contradictory narratives, mistyped section can significantly impair the effectiveness of decision support systems. Addressing this Addressing these challenges is crucial for reliable outcomes. Beyond accuracy, completeness, consistency, we propose two additional dimensions vital for legal analytics: timeliness, which ensures that data is current and relevant, and verifiability, provenance, which traces the origin and modification of data for authenticity. So there are the following challenges we should keep in mind, that is accuracy issues, mixed type sections, factual errors, completeness concern, missing timestamps, incomplete narratives, consistency challenges, contradictory complaint details, new dimensional timeliness, up to date data, variability, verifiability, data origin and modification. And there are the following strategies for handling missing value. As for making assumptions and decision making, the dataset has to be complete. So handling missing value, we can do the following things: ignore tuples. We can drop that row or the tuple, but it can lead to significant data loss if the complaints have missing value, if many complaints have. Manual completion, time consuming it is, but ensures accuracy and feasibility for small data set. Constant fill, replace with predefined constant, but it introduce bias, as everything in universe has some variation or disturbance or noise. It can't follow a single rule. There will be variation in everything. Mean, median, mode imputation. Here, these statistical methods can be used for imputation, but mean is prone to outliers. Mode is not about the centrality of the data, but median is the best choice here we can do. Class specific imputation. Impute based on the offense category, ensure more relevant replacement. Most probable value. Use a predictive model to estimate a missing value, offering higher accuracy. For smoothing extracted scores and outlier detection, we have these following methods. So, smoothing extracted scores is particularly for evidence strength, is essential to reduce noise and reveal underlying pattern. Outlier detection is equally critical, as rare but high impact cases with low evidence can significantly distort result. This section explored methods for both smoothing and identifying anomalies. Suppose if we have a data set having outliers that are way bigger than the normal data, it can lead to abnormal mean values. So hence all these methods are important. Smoothing with bean means def 3. So here is the data set, and we have chosen 3. We have made 4 beans of each having 3 data set, and we have calculated mean of everything, every bean. And here's what the bin is. You can see this is smoothing with bin methods. For outlier detection, we have statistical method like z-score, IQR. In IQR is also a good method in that it was significantly deviating from the norm. Domain expertise: consult legal experts to identify threshold for rare, very high impact cases with low evidence. Clustering isolates the data points that do not fit into any cluster, suggesting their anomalies. Other smoothing methods include bin medians, locally estimated scatter plot smoothing, moving averages, robust estimators, and many other things. So, moving towards the next topic, we have schema integration and conflict resolution, in which the complex system like DSS integrating diverse data sources such as EFIR and physical logs often leads to schema integration challenges, redundant entries, and value conflicts. Effectively managing these issues is crucial for maintaining a unified and accurate knowledge base. Redundancies can lead to inefficiencies, while value conflicts can introduce inconsistency and error in the system's output. So, if we want to use a data set to its full potential, the data set has to be structured, and there should be data integrity, data consistency, less redundancy. So for the first thing is data integration, schema integration, merging different data schemas into a cohesive unified structure. This involves identifying common entities, attributes across various sources, and resolving naming conventions and data types. Handling redundant entries, detecting and removing duplicate entries across different data sources, example EFIR and physical logs, to prevent data inconsistencies and improve data quality. This often involves fuzzy matching algorithms. Moving to the third point, which is resolving value conflicts, addressing discrepancies in data values for the same entity across different sources. Example include differing monetary loss figures or such labels for the same incident, requiring predefined values and manual review for resolution. So now for normalization methods for feature scaling. Feature scaling through normalization is a critical pre-processing step in data analysis, ensuring that all features contribute equally to the model by bringing them to a common scale. This prevents features with larger numerical ranges from dominating those with smaller ranges, leading to more stable and efficient model training. For example, if we have an attribute age and if we have an attribute salary, so there will be a very huge difference in the value of both attributes. So normalization is done to maintain uniformity, or so that all features can contribute equally. So the first, in order to normalize a data using min-max normalization, we just calculate the difference between the data and the minimum value of the data set and divide it by the range of the data set, which is calculated as the maximum value minus the minimum value. And for the z-score normalization, we calculate the mean of the data set, then we calculate the difference of each data item to and the mean and divide by standard deviation. So this is how we do all these things. And the scale of min-max normalization ranges from 0 to 1. As for the z-score normalization, it is also from, it transforms the data to have a mean of 0 and a standard deviation of 1. So z-score using mean absolute deviation is a more robust alternative to standard deviation for outlier prone data. Suppose if we have a data having outliers, we can use mean absolute deviation. Decimal scaling normalizes by moving the decimal point of value suitable for positive numbers. And the choice of normalizing method depends on the data distribution, what kind of data we have. If we have data without outliers, we can easily use the z-score normalization. The specific requirement of machine learning algorithm being used is also considered. Proper scaling is fundamental for accurate model performance. Binning case severity score. So here, binning or discretization transforms continuous numerical data into categorical bins. We have a numerical data and now we convert that data into categorical different categories, simplifying data interpretation and improving model performance. For case sensitive scores, different binning strategies yield varying distributions and implication for section mapping and threshold. So let's take this example. And for equal frequency bins, where each bin contains equal number of data points. So here you can see 4 bins are created in which every one of these have equal number of data set, and it ensures balanced representation across severity levels, but bin widths can vary greatly. The second one is equal width binning. In this, each bin covers the same range of score values, and this is calculated by calculating the difference between the largest data in the bin and the smallest data, and then dividing it by the total number of bins. So each bin gets data in the same range of scored values. So here you can see the first bin will have data from 5 to 57.5, and the values in between this range is 5, 10, 11, 13, 15 and 35, 50, 55. The second bin will have a 57.5 to 57.5 into 2, which is 110. It contains 72 and 92, and in the second there is 110 and 165.5, 62.5. In this range there is no value, so this bin is left empty. And in the fourth bin we have a 204 and 215. So here the bin frequency can differ, but this is simple to interpret, and some bins might be sparse, especially for skewed data. Cluster based bin. Group scores based on their proximity, creating natural clusters. It requires algorithm to determine the cluster. Here the categorical data is stored in different clusters, and these clusters and the assignment to this cluster are determined by the clustering algorithm. Here you mean k-means clustering, k-based clustering. So these bins reflect intrinsic data structure, potentially leading to more meaningful section mapping and threshold. Each binning method has a direct implication for how the DSS sets threshold for section mapping, influencing the granularity and sensitivity of classification we choose. The model is vital for the accuracy and practical utility of legal insights generated. Now, feature selection for section mapping. Feature selection is crucial for optimizing the DSS by identifying the most relevant attribute for accurate IPC and BNA section mapping. Here these features will determine the performance. These are directly related to the output. This process reduces dimensionality. Here we suppose if we have 100 attributes. Now using feature selection we use a relatively smaller data set, maybe 20 attributes, that are the most important ones, and that defines the overall variability of the data sets from which it comes, which is enough. So this is dimensionality reduction, and it improves model performance and enhances interpretability. It explores key techniques with a flowchart. We explore key techniques with a flowchart summary. So for this, there happens forward selection, then there is backward elimination, then hybrid method. In forward selection, it is a greedy iterative approach for feature selection. It begins with an empty set of features. In each iteration, adds the feature that provides the most significant improvement to the model performance until no further improvement is observed. This method is computationally less expensive than backward elimination, as we don't have to repeat the steps for very large feature sets, but can miss optimal combinations. So we first start with an empty set, then we evaluate the individual features and see what features makes the most significant improvement to the model performance. Then we add the best feature based on the greatest performance improvement that is added to the set, and then we repeat until there is no improvement. The process continues until adding any more feature does not significantly enhance the model performance. Talking about the backward elimination and hybrid method, while forward selection builds up a feature set, backward elimination works in reverse. Starting with all features, it progressively removes the least useful ones. We in forward we were adding up features. Now in backward we are removing features that are not that much useful. The hybrid method combines both strategies, aiming for a balance between computational efficiency and thoroughness. Both methods are invaluable for refining the DS's ability to map complaints to IPC BNS sections accurately. Backward elimination In backward elimination, we start with all candidate features and iteratively removes the less significant feature at each step. This process stops when the removal of any further feature causes a significant degradation in model performance. So, yeah, we just start with a bag full of features, then we identify and remove the feature which contribute less to the model performance, and the performance of model won't be affected by the removal of this one, and we repeat the steps until the removal of the specific features has a significant loss. In hybrid method, it is a blend of forward and backward elimination. The hybrid method often provides a more robust feature set. It add a feature using forward selection and then check if the existing feature can be removed without harming the performance, similar to backward elimination. So utilize steps from first. We select the feature using forward selection, then we do backward selection. This is how we achieve a balance between compact feature sets and optimal performance. Continuously add and remove feature until the best combination is found. So this is all done for feature selection, so that our model gets is the best set of features and it yields to great output. So with this I would like to end this presentation. Thank you so much for listening to this video with so much patience. This is the answer for the C section of first internal data science examination. Thank you.